Okay, so we're at the very end of the course. This is really the last week of new lecture content. Next week, we're just going to be covering some exam review material. So we're going to go over everything again really briefly. But this week is the last week of new content, and it's going to be Gravity Part 1 and Gravity Part 2 on Friday. So far, when we've been talking about, let's say, force of gravity or the gravitational potential energy, so that's where gravity has come up so far, we've always been talking about objects that are close to the surface of the Earth, so down here, close to the Earth. But today we're going to talk about what happens when objects are not close to the surface of the Earth. We can't use the acceleration due to gravity as 9.80 meters per second squared anymore, because that's only applicable if you're close to the surface of the Earth. Okay, so we're going to talk about how we can approach questions like that when we're no longer close to the surface of the Earth. So we're going to talk about Newton's law of gravity. We'll talk about where the formula for G, or that 9.80 meters per second squared, where did that come from? How can we calculate that, particularly when we're in different locations, like not close to the surface of the Earth? And then we're going to talk about gravitational potential energy. So we've already talked about gravitational potential energy before when we were near the Earth. So the formula, does anybody know what the formula was for UG equals?
MGH.
Yeah, good, MGH. Now, the G is no longer going to be 9.8, and the formula we use is no longer going to be MGH anymore. Okay, so we're going to have to change that formula around. We're going to talk about how to calculate the force of gravity when we have a system that has 3 or even more objects. Okay, and then you'll have time to do your homework, which includes the quiz. So I have received some emails from people who are having a difficult time completing their quizzes on time. Everybody has different situations. So some people have difficulty getting like good internet connection. So that's like an extra challenge that they're faced with. Some people have children that, the schools are closed, and I have children too. Schools are closed, and we have to manage our kids while we're trying to manage our own work. So it's like extra challenges. So I thought, just to try to alleviate a little bit of stress, I'm going to make the quizzes due a day later than they normally are. So rather than being due tomorrow night at midnight, today is Wednesday, so they'll be due on Friday night at midnight. And then the Friday quiz will be due Sunday night at midnight. Okay, so you'll just have an extra day. Everything else is the same. If you want to complete it on time, that's great. But if you need that extra day, then I'm happy to give that. Okay, if there's anything else that you think would help you that I can do without really like sacrificing the integrity of the course, like I want you all to learn everything you need to learn so that you'll be ready for physics 2 or whatever else comes your way. I don't want to sacrifice that, and I don't want to sacrifice like the academic integrity of the course. But otherwise, if there's anything I can do, please let me know. You can email me or you can ask me right now. I'm happy to think of ways, like explore ways to make this transition easier for you, because I know it's been difficult for me. It's difficult for all instructors, and it's, I'm sure, very difficult for you as well. So please let me know if there's anything you think I can do to help. Okay. Does anybody want to speak up about that at all? Okay, we'll move on, but please feel free to email me if you want to talk privately, or we can set up an appointment and meet on Google Meet. Okay. So, Newton's law of gravity. All right, so far, when we talk about gravity, we've always been talking about the force that's acting on an object. And the object so far has been close to the surface of the Earth, and it's really the force that's been between the object and the Earth. So the Earth and the object are attracted to one another because the object has such a smaller mass compared to the Earth. The object feels that acceleration, it feels the force much more than the Earth will. In fact, the two forces that are acting, so the force that's acting on the object and the force that's acting on the Earth, are equal to each other. This is Newton's third law. Every action must have an equal but opposite reaction. They're two equal forces, but because the mass of the Earth is so huge, the acceleration of the Earth is tiny, because F net equals ma, so acceleration is F net over m. So because the mass of the Earth is really big, its acceleration would be small. So like myself standing near the Earth is not making the Earth accelerate very quickly towards me, but myself standing near the Earth is making me accelerate towards the Earth. So if I'm standing on top of a bridge and I want to bungee jump off, I'm going to be accelerating very quickly towards the Earth, right? And that's because my mass is so small in comparison to the Earth's mass. So we feel the force of gravity acting on us, but in fact, there's a force of gravity that acts between any two objects. So between me and my computer right now, there's a force of attraction between us. The force of gravity is always an attractive force. That's why for force of gravity, we always say it points down, but that's only the case because we're talking about force of gravity between an object and the Earth. And the Earth is always down in relation to the object, right? But if we think of any two objects, there is a gravitational force that's pulling those two objects together as well. It's just going to be a lot smaller compared to the force that the Earth pulls on the object. So we don't really notice it, but there are forces that are pulling us and every object towards each other. Okay, so every object in the universe attracts every other object in the universe with a force that's inversely proportional to the square of the distance between the objects, which means if the objects are closer to each other, the force gets much bigger. If the objects are farther from each other, the force gets much smaller. And the force is also directly proportional to the masses of each object, which means the bigger the masses are, the bigger the forces are going to be. That's why we feel forces with big objects. So between us and the Earth, we feel that force. That force is really big that pulls us towards the Earth. But we don't really feel the force that's pulling us towards our computer screen right now because our mass and the computer screen's mass is not very big compared to the mass of the Earth. Okay, so according to Newton's third law, for every force exerted by an object, there's an equal but opposite force exerted on it by another object. So if we have two masses, mass 1 and mass 2, and their centers are a distance r apart from each other, okay? So some distance that we're calling r is the distance between the centers of the two objects. If we have these two objects, they each have to exert a force of attraction on one another. And the magnitude of that force we call the force of 1 on 2. So when we see F12, that means the force that object 1 exerts on object 2 is equal to this gravitational constant here, which is written below. It's equal to 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared times the mass of each of the two objects in kilograms divided by the distance between the centers of the two objects squared, where the distance is in meters. Okay, so that's the general formula. That's written on your formula sheet. It's the gravitational force between any two objects. So we're going to practice with this one question here. Find the force of gravity acting on a 2.5 kilogram block that is on the ground. The mass of the Earth is 5.97 times 10 to the 24 kilograms, and its radius is 6.37 times 10 to the 6 meters. Okay, notice for this question, the object is close to the surface of the Earth. It's on the ground. So when we find the force of gravity, we can do it the old way, the way we've been doing it all along. What was that formula? Fg equals what's the formula we've been using all along to find Fg?
mg.
Good, mg. The object is 2.5 kilograms. And what's g?
9.80.
Yeah, 9.80 newtons per kilogram, which is the same as meters per second squared. Okay, so when we multiply these, 2.5 times 9.8, we get 24.5 newtons because the kilograms cancel. So that's the force of gravity. We don't need to use any special equation because this object is close to the surface of the Earth. But we can use the other equation and we should get a similar answer. So let's try using the other equation. Fg equals the formula from above. So we have g times mass 1 times mass 2 over r squared. So G is this constant over here. So we can just plug in that number. M1 is the mass of the first object. So again, we're talking about the force of attraction between the block and the Earth. So we have a 2.5 kilogram block and the Earth, which is 5.97 times 10 to the 24 kilograms. All over their distance, which means the distance between their centers squared. So here's the Earth, and here's the block sitting on the surface of the Earth. What would we put in for R, the distance between the center of the block and the center of the Earth? What do you think the value of, oh, sorry, I have a dog. What do you think the value of R should be here?
Should it be 6.37 times 10 to the
Yeah,
6?
good. So the center of the Earth to the surface of the Earth is that 6.37. That's the radius of the Earth. And the object, the block, is so small in comparison that we can just ignore that. Okay, so I'm going to put for my R just the 6.37 times 10 to the 6 meters. And we don't need to worry about the size of the block because it's so small in comparison. And all of that on the bottom is squared. Okay, so I'm going to type all of that up and see how that number compares. So I have 6.67 times 10 to the negative 11 times 2.5 times 5.97 times 10 to the 24 divided by 6.37 times 10 to the 6 squared. And we get 24.53 really. So I'm going to just round it to 3 significant digits and it's the same value, 24.5 newtons. So do you see, it doesn't matter which formula we use when we're close to the surface of the Earth, we might as well just use the easy formula, Fg equals mg. Okay, but the other formula will always work anyways. Now we're going to move on to question 2, and you're going to tell me which formula we have to use for this one. So we want to know the force of attraction between a 50 kilogram woman and a 70 kilogram man that are sitting 100 or 1.5 meters apart. So we're going to assume that this distance is the distance between the two centers of the people. The center of the woman and the center of the man are 1.5 meters apart from each other. So when we calculate the force of attraction, we're really looking for that gravitational force. Are we going to use Fg equals mg, or are we going to use Fg equals g m1 m2 over r squared?
Use the second formula.
Yeah, exactly. So we're going to have to use the second one because we're not talking about the force of gravity between the person or the object and the Earth. We're talking about the force of attraction between two objects. So we have to use the second one. Do you think that this number is going to be a really big number or a really small number? The force of attraction between two people. Do you think it's going to be really big or very small?
Very small.
Yeah, it's really small. Like we don't notice that we're being pulled towards somebody else, but it does happen. It's just so small that we don't notice it. So I'm going to write the force. I could call it the force of gravity, or I could call it the force between object 1 and object 2. They're both the same thing. Gravity is the force of attraction between two objects. We normally think of it as the force of attraction between an object and the Earth, but it can be between any two objects. So it equals G mass 1 times mass 2 over the distance between the two object centers squared. So G is a constant, 6.67 times 10 to the negative 11. Mass 1 is the 50, I'll say the woman is mass 1 kilogram woman, and the 70 kilogram man is mass 2. And the distance between their centers we're going to assume is just 1.5 meters apart, and it's squared. So I'm just going to type this up, 6.67 times 10 to the negative 11 times 50 times 70 divided by 1.5 squared. So I get 0.000000104 newtons. Okay? On a test, you can just write it just like this. You can leave your answer like this. In Numbus, or like on the online quizzes that you do, it's actually, that software is actually pretty smart. It understands the prefixes. So on the quiz itself that you're going to write today, it will say enter your answer in normal form using as many trailing or leading zeros as needed. So saying like just enter all these zeros in yourself. It doesn't matter if there's like a bunch of them, just enter them all in. Your other option is to use prefixes. So if you want, you can move the decimal place, let's say 1, 2, 3, 4, 5, 6. You can even go further, 7, 8, 9, let's say. So 104, if you move it over 9 times, what's that prefix for it to be times 10 to the negative 9?
Is it nano?
Yeah, good. So you could write nanonewtons and it would understand that. Okay, you could also write 0.104. Then I just moved it over 6 times. So what's that prefix?
Milli?
Close. That would be for 3 times. That would be a little m for milli. But 6
Micro?
times, yeah, micro. So that will just be a little u, micronewtons. Okay, so on your online quizzes, you could use prefixes, and it tells you in the question itself, either write down all the leading or trailing zeros as needed, or enter prefixes if you like, if you don't want to enter all those zeros. Okay, on Blackboard, when you write your tests, just put in all the zeros. Okay. Any questions there? Actually, this is not going to be on a test. It's only going to be on your final exam. And it will likely be like we're going to be marking your solutions, or it's going to be multiple choice. So you don't really need to worry about whether you entered in like whether you like make a mistake with one of your zeros, for example. As long as your solutions are correct, you're good to go. Okay. If it's multiple choice, it really doesn't matter because you're just going to have to see what the choices are and select the correct answer. So you don't have to worry how to enter the question, how to enter the answer. Any questions there? So on your quiz that's today, just either enter all the zeros as needed or use like the micro or the nano, or if it's a really big number, you can use the kilo or the mega or the giga, all of those prefixes because it understands those. Okay, or just use all the zeros if you want. Okay, since the gravitational force between two ordinary size objects is so small in comparison to the gravitational force exerted on these objects by the Earth, they're virtually undetectable. So meaning we don't really notice the force of attraction between us and our computer right now because the force between us and the Earth is so much bigger in comparison. So the question is asking us to calculate the gravitational force that the Earth exerts on a 50-kilogram woman. The mass of the Earth is given and its radius is given. Okay, those numbers will be given on a formula sheet or on the test itself. You do not have to memorize these numbers, the mass of the Earth and the radius of the Earth. Okay, so I want you to find this gravitational force. The formula again, so force of gravity is equal to G m1 m2 over r squared. By m1, we're talking about the woman, that 50 kilograms, that would be m1. M2, we're talking about the Earth because we're finding the force of gravity between the woman and the Earth. So this would be our M2. And then, sorry, my dog sees something. And then, what are we going to use for the radius? It would just be the 6.37 times 10 to the 6. Okay, so I'm going to give you a minute to calculate this while I make my dog move. All right, I'll be right back. Silence. Okay, I'm back. So I'm going to just enter in all these numbers. Now, just to confirm everybody understands this R value, this is the Earth. This is the lady, the woman that's on top of the Earth. The R value is the distance from the center of one object, the woman, and the center of the other object, the Earth. So here's the center of the woman, and here's the center of the Earth. Of course, this isn't drawn to scale though. The woman is way tinier than the Earth. So the radius is really just the radius of the Earth, because the woman's size, right, her volume is really, really small compared to the radius of the Earth. So we can just ignore it. So the R value we're using in this equation is just the radius of the Earth. Does anybody have any questions here? Can somebody speak so I know you can hear me?
Oh, we can hear you.
Thank you. Any questions though? Okay, I'm just typing everything into my calculator. And I'm getting 490.67. I'm just going to round it. So it would be 490. If I want this to be significant, I can put the decimal here. And then my units is newtons, or I can write 4.90 times 10 to the 2 newtons. Again, if you're writing this on a test or on a quiz, don't worry about the significant digit. Like for this situation, just write 490 newtons. Okay, in your solutions, you can write down the decimal or the 4.90 times 10 to the 2 so that you have 3 significant figures. Is that clear? Any questions? Okay, so this question here is saying that the force of gravity that's exerted by the Earth onto the woman is 490 newtons. If we go back to the last question, the force of gravity between the woman and the man, so this is the same woman, okay? There's a 70 kilogram man. The force that she feels that the man exerts onto her is 0.0000104 newtons. And she feels a force of gravity that the Earth exerts on her of 490 newtons. So of course, the force of gravity that the man exerts on the woman is negligible compared to the force that she feels that's exerted on her by the Earth. Okay, that's why we don't notice these other forces, because they're so small, right? Like my dresser and I have a force of attraction, but it's so small compared to the force that the Earth is pulling down on me. Okay. Number 4. A truck has 4 times the mass of a motorcycle. If the magnitude of the force of the truck on the motorcycle is 0.0214 newtons, what is the magnitude of the force of the motorcycle on the truck? So just take a moment to read this question again, think about it, and let me know what you think. So what do you think? What's the magnitude of the force of the motorcycle on the truck? If the force of the truck on the motorcycle is 0.0214 newtons, what's the magnitude of the force of the motorcycle on the truck? Is it going to be bigger or smaller?
Will it remain the same?
Yes, it will remain the same, because remember Newton's third law. The force that the motorcycle exerts on the truck is equal to the force that the truck exerts on the motorcycle. The forces are the same. It's the accelerations that are different, because if we use Newton's second law, F net equals ma, if the mass is big, then the acceleration will be small. right? So it's just like what I was saying about us and the Earth. The force of attraction between us and the Earth is the same whether we're talking about the force exerted on me or the force exerted on the Earth. The force that I exert on the Earth is equal, but opposite in direction to the force that the Earth exerts on me. We have equal forces acting on us, but the Earth has a smaller acceleration because its mass is so big. So it doesn't really notice. We don't see the Earth accelerating towards us in the same fashion that we accelerate towards it. Okay, so the forces are always equal. It doesn't matter whether one object has a bigger mass or not. Okay, any questions there? So the answer is just 0.0214 newtons because the force of the motorcycle on the truck is equal to the force of the truck on the motorcycle. And the question's asking for what is the force of the motorcycle on the truck. So it's written like force motorcycle on the truck. Okay, so it's kind of tricky, like it's kind of not super intuitive, but the forces for action force equals the reaction force. They're equal but opposite. Okay, so for Fg, we've always talked about Fg equals mg when we're trying to find the force of gravity exerted on an object with a mass. And in every case, the objects so far in this class have been close to the surface of the Earth. So we've always said that g is equal to 9.8 meters per second squared, or 9.8 newtons per kilogram. But where did we get that value of g? Okay, so we're going to take a look at Newton's law of gravity, which is the longer equation. F of g, or F, the force between two objects, is equal to g m1 m2 over r squared. Okay, so if we were talking about the force of gravity that the Earth exerts on an object, it would equal g, and then the mass, we have two masses here. We have the Earth and the object. So we have g times mass of the Earth times mass of the object divided by the distance between the two objects. And we're going to still assume that the r value is the radius of the Earth because we're saying the object is close to the surface of the Earth squared. Okay, so in this next equation here, all that we've done was replaced r with radius of the Earth. Again, because we have, here's our Earth, here's an object that's sitting on the surface of the Earth, and the distance between the center of the Earth and the center of the object is really just the radius of the Earth, because the size of the object is negligible. Okay, now Fg is also equal to mg. Right? And when we did this equation, Fg equals mg, which mass were we referring to? Is that the mass of the object or is that the mass of the Earth?
Mass of the object.
Right, like if I told you I have a 2 kilogram object and I wanted you to draw a free body diagram of it while it's just kind of being thrown in the air. So the only force acting on it is the force of gravity, and we'd say Fg equals mg, which is 2 times 9.8, right? So the mass of the object is 2. So this mass is referring to the mass of the object. So in this equation that says Fg equals gm Earth m object over r Earth squared, Fg is also equal to mg, m of the object, times g. So that takes us to this equation here. The same thing, Fg is equal to two different equations, the long equation on the left and the smaller, the shorter equation on the right. Does that make sense so far? So we're just taking the two equations for Fg and setting them equal to each other. We're talking about an object that's close to the surface of the Earth, and we're trying to solve for this g over here. So if we were to divide both sides by the mass of the object, we can see that this mass cancels out. And then when we solve for g then, we're left with capital G, mass of the Earth, over radius of the Earth squared. So if we start to put in the actual numbers for the Earth, so g is that constant 6.67 times 10 to the negative 11. Mass of the Earth, we have it up here, I think. this value 5.97 times 10 to the 24. And the radius of the Earth is also up here given in the question, 6.37 times 10 to the 6. So if we type this up, what do you think we should be getting? A number close to what? We're solving for g close to the surface of the Earth. What is g that we normally use when we're close to the surface of the Earth?
9.81.
Yeah, so we should be getting a number that's close to 9.8. So let's see. So yeah, when I type it up, I get 9.8134. And that's why we're using a value. So in this class, we're kind of rounding it. We're saying it's 9.8. Okay, it's very similar, meters per second squared. So that's where this number is coming from. Now, of course, on Earth, the radius is not like these values, 6.67, 5.97, and 6.37, they're not exactly correct, like they're rounded a little bit. And also the Earth is not a perfect sphere, like it's a little bit longer in one direction than another. So perhaps like this number is a little bit off, but the reason why it's so close is because of this formula and these values we're plugging in. Okay, so if I wanted you to find the little g, so the acceleration due to gravity on another planet, then all you need to know is the mass of that planet and the radius of that planet and plug all of those into this equation and you can get your little g. Does that make sense? Let's move on. Next one. Number 5, calculate the acceleration due to gravity for an object that is at various locations. The mass of the Earth and the radius of the Earth is given, the mass of the moon is given, and the radius of the moon is given. So we want to know the acceleration due to gravity, so that little g, which is equal to g times the mass of, I'll just write the planet or the moon, like whatever the celestial body is, over r squared, where r is the distance from the center of the object to the center of the celestial body. So all of that equals g, which is 6.67 times 10 to the negative 11, times the mass of the Earth, which is 5.97 times 10 to the 24th, divided by the distance squared, where r is 6.37 times 10 to the 6, all squared, which equals 9.80 meters per second squared. So what happens if we're on top of a slide? Everything's going to be the same, except what are we going to enter for the radius this time?
Minus 30 meter.
Minus 30 meters? I believe it's plus 5 meters.
Yeah, so the
Oh,
radius, yeah, if we kind of draw a picture of what's happening, this is the Earth, and this is the slide on top of the Earth, okay? Obviously not to scale. The slide is 5 meters in height, and the radius of the Earth is given, the 6.37 times 10 to the 6. So the r value is the distance from the center of one object to the center of the other object, and the object is on top of the slide over here. So the center of the object to the center of the Earth would be this full value here. So what would we put down for the r value?
R plus 5 meters.
Yeah, good. So it would be, this is still the mass, 5.97 times 10 to the 24. And then on the bottom, we have the radius of the Earth, which is 6.37 times 10 to the 6 plus 5. And then all of that is squared. Now, is that 5 going to make a difference? Is it going to make a significant difference?
Not a significant difference, but
No. We can type it up. What do we get when we type it? So when I enter just 6.37 times 10 to the 6 in the denominator, I get 9.81344. And then when I enter 6.37 times 10 to the 6 plus 5 in the denominator, then I get 9.813. Okay, so this is just to demonstrate that whether you're on the surface of the Earth or whether you're on top of a slide that's 5 meters above the surface of the Earth, your g, your gravitational like acceleration due to gravity, is still going to be like the same roughly. Like there'll be a tiny difference way down many digits later, but it's not significant enough for you to even worry about. So this is telling us that if we need to find the force of gravity for an object that's near the surface of the Earth, we could just write Fg equals mg, where g is just 9.8. Okay, we don't need to use like 9.813. We can just use 9.8 like normal. If the object is on top of a slide that's 5 meters tall, we can still just say the force of gravity acting on the object is mg, the mass of the object times 9.8, okay? Because the 9.8 number is not changing when we're close to the surface of the Earth. So when I say close, what do you think I mean? So near the surface of the Earth, so you're actually on it, that's close to the surface of the Earth. On top of a 5 meter tall slide, that's still close to the surface of the Earth. Do you think on top of a building that's 30 meters above the surface of the Earth is still close?
Not really. It's still
Okay,
a
so let's
small
try
number.
it. Yeah. So let's find out what this number, are you saying it's close or it's not close?
It's not. It's still gonna be relatively close to 9.81.
Yeah, exactly. So if we do this number here, 6.37 times 10 to the 6, and then plus the 30 squared equals, so now I'm just going to rewrite everything but with the 30 on the bottom. And I still get 9.813. So in all these cases, we can just use g equals 9.8 meters per second squared. What happens if we are now orbiting the Earth a distance of 1350 kilometers above the surface of the Earth? Do you think we can still use g equals 9.8 meters per second squared?
No.
No, now it's really far away, right? So let's find out what our g would be in this case. G equals 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 over 6.37 times 10 to the 6 plus, now what am I adding here?
Well, 1,350,000.
Yeah.
100,000.
Good. Because it's in kilometers, so I have to add 3 extra zeros at the end, and then squared. Okay, so now when I do that, on my calculator, I'm going to check to see what I get here. So now I'm getting 6.68 meters per second squared. So now we cannot use g equals 9.80 meters per second squared anymore. We're way too far away from the surface of the Earth. So when we say close to the surface of the Earth, we mean, you know, if you're on a slide, on a building, okay, if you're on a tree, something like that, you're close to the surface of the Earth. But as soon as you're like a kilometer or more away from the surface of the Earth, you can't use 9.8 anymore, okay, for g. You have to calculate it using this method. Okay, and now we can do on the surface of the moon. So we're on the surface of something, but it's not the Earth anymore, so we can't use 9.8. So we're going to use the numbers for the moon. 6.67 times 10 to the negative 11 times the mass of the moon, which is 7.36 times 10 to the 23 divided by the radius of the moon, 1.74 times 10 to the 6 squared. So I'm getting this value here. I'm feeling a little bit uncomfortable with this number. I feel like it's a bit high. So I might have my facts wrong here about the mass of the moon or the radius of the moon. It might be like, I might be off by a factor of 10 here. Next, we're going to move on to gravitational potential energy. So before, we used to use this formula, UG equals mgh, to determine the gravitational potential energy of an object. But that formula is only object when you're trying to find the gravitational potential energy between the Earth, typo, and the object that is close to the surface of the Earth. Okay, if the object is far from the Earth, or if you're trying to find the gravitational potential energy between two other random objects, just like we did between the man and the woman, right, that didn't have any chemistry, then in that case, then we would have to use a different formula. We couldn't use mgh anymore. Okay, so the new formula is over here. Gravitational potential energy is equal to negative, and the negative is important, g, which is that same constant that's given to you, 6.67 times 10 to the negative 11, times mass 1 times mass 2 over r. So this time the r is not squared, like it was with the FG formula. Okay. So it's all very similar to what we did with the force, but now we're calculating gravitational potential energy. Remember, we did conservation of energy questions. We did a lot of conservation of energy where, for example, a boy is sliding down a slide. He starts at the top of the slide with gravitational potential energy. He gets to the bottom of the slide, and now he has kinetic energy. Okay. In that question, the boy is close to the surface of the Earth at all times in the whole problem. So we can just use mgh when we're doing gravitational potential energy. But if we were talking about like a meteor that's going to shoot out and crash onto the Earth. So at one instance, it was like thousands of kilometers away, and then at the end of the story, it's now crashed into the Earth. What is its velocity? Okay, so when we're using conservation of energy in a situation like that, the object is not close to the surface of the Earth for the entirety of the whole problem. So we have to use this formula for UG. Okay. Now the negative sign, let's address it. So if we were using UG equals mgh, so we have a boy on a slide. He's up here, and then he slides down. He gets up down there. So initially he's here, final he's at the bottom of the slide. Obviously not to scale. This is the slide, and this is the Earth. So it's obviously not to scale. So when the boy is at a higher height, so initially, is his UG going to be bigger or is it going to be smaller than when he's at the ground? Is it bigger than UG final or is it smaller than UG final?
Bigger.
Yeah, because mgh, so his height is higher over here. Let's say this is our reference height at the bottom, then initially his height is higher than his height at the bottom. So UG initial is bigger than UG final. Now that has to be true no matter which formula we use. Gravitational potential energy when you're at a higher height has to be bigger than when you're at a lower height. Does that make sense? Your gravitational potential energy, any potential energy, means the potential for you to actually move, okay, to do work, which means you're moving. So an object has more potential to move and to move quickly if it's at a higher height. So if you're on top of a bridge and you're going to bungee jump off, you're going to move really quickly when you jump off compared to an object that is like only on a step ladder. It's not going to go quite as fast when it hits the ground because it didn't start from a higher, as high a position. So the higher you are, the more gravitational potential energy you have, the more potential you have to do work or to move really quickly, to have a high velocity. Does that make sense? When you look at the formula, UG equals mgh, that tells us the same thing. The bigger the h is, the bigger the UG is going to be. Now, when we look at this new formula, let's think of the same thing. Let's say this is the surface of the Earth, and now we're over here. So r is the distance from the center of the Earth to the center of the object. Let me redraw this. Give some space. Okay, so let's say this is the Earth, and now we're all the way out here somewhere, and this is our r value. So this is our r initial. And then later, let's say we're down here. So this is our r final. So we would still expect that the UG initial should be bigger than the UG final, because initially we're farther away from the surface of the Earth. We have a bigger height, right? So we should have more gravitational potential energy. But when you look at the formula here, as R gets bigger, if we ignored this minus sign altogether, as R gets bigger, what would happen to UG? Would it get bigger or smaller?
Smaller?
Good. I was going to check if I muted myself. Okay, good. As R gets bigger, then UG gets smaller. And that's not what we want, right? The farther you are from the surface of the Earth, you should have more gravitational potential energy, not less. And that's why there's this negative sign in here. The negative means that as R gets bigger, UG actually gets bigger because it becomes less negative. Does that make sense? So the number, as R gets bigger, UG becomes a smaller absolute value, but there's a negative in front of it. So it's getting less negative, so it's actually increasing. So that negative is very, very important to keep in there.
Sorry, Caroline, can you substitute fractions, substitute numbers for illustration?
Like, what do you mean by fraction where? For R?
For R, yeah. Let's say it starts with 2, then it becomes 4.
Yeah, sure. So let's say initially my R value was 4, which doesn't really make sense because 4 meters is more than the radius of the Earth. I mean, less than the radius, but let's say 4 meters. And then at the end, now we're only 2 meters. So the R value went down, right? So when we plug into the formula, negative G M1 M2 over 4 compared to I'll do it for, so this is UG at R equals 4 or UG at R equals 2. I'd have the same equation, G M1 M2 over 2. Which number is bigger? When you divide by 4, you get a smaller number, but it's negative. So this number is actually bigger. Okay, just like if we were to say negative a quarter compared to negative a half. Negative a quarter is negative 0.25. and negative a half is negative 0.5. If we drew that on a number line, negative 0.25, let me draw it somewhere else. Let's say this is 0, negative 0.25, negative 0.5 is smaller, right? The absolute value of negative 0.5 is bigger, but because it's negative, it's a smaller value than negative 0.25. So the whole idea here that I'm trying to explain is that the negative here is very important. Without the negative, as R gets bigger, the UG would get smaller, which is incorrect. We need the negative sign so that as R gets bigger, the UG gets bigger as well because it becomes less negative. Any questions? I can go over it again if anyone's unclear.
It's clear.
Okay, thank you. Okay, so what's really important is to remember that negative sign because it's really easy to forget it. And also, if you're using a conservation of energy, if you're doing a conservation of energy problem, and let's say you have gravitational potential energy initially and at the end, final, you have to use the same equation both times. So you can't use MGH initial because the object's close to the surface of the Earth initially. And then later, the object is far from the surface of the Earth. So now you use the negative GM1 M2 over R equation. You can't do that. You either have to use the MGH equation all the time or this equation all the time. So if at any point in the problem, an object is not close to the surface of the Earth, you use this bigger equation for initial and final, no matter whether it's close to the surface at one point or not. Okay, so you can't mix and match the two equations in one conservation of energy solution. Does that make sense?
Yes.
Thank you. Okay. So remember when we talked about UG equals MGH, and we said, okay, sometimes when we do E total initial equals E total final, let's say if we had EK plus UG initial equals EK final. Let's say there's no spring in this question, so I'm ignoring elastic potential, UG final. Sometimes we'd say, oh, okay, let's cross off this one because there's no UG initial. When is it that we're able to cross off UG initial? When the height is?
0.
Right. When we define, let's say this is a slide, this is the boy at the top of the slide, and we say the initial height or the final height here is 0, the initial height is 5 meters or something. Well, we'd say, okay, well, the final height is 0. So because the final height is 0, then UG final is 0. We can cross it out completely, right? In this case, when we're using this formula, what is the value of R that allows us to cross off UG to make it 0? When will UG be 0? For what value of R?
Like a really huge.
Exactly. Good. Exactly. Okay. So as R approaches infinity, so if we say the object is very far away from the surface of the Earth, that means it's approaching infinity, and so UG is 0. So that's the time now where we can say UG is 0. It's kind of the opposite of what we used to do before. Before, when the object had a height of 0, we said UG is 0. Now, when the object is infinitely far away, that's when UG is 0. Okay, and that's because of that negative sign. It's just changing the frame of reference. Okay, so we're going to complete conservation of energy problems using this formula in our next lecture, okay? Because in the next lecture, we're going to have some problems where the object is not always close to the surface of the Earth, so we can't use UG equals MGH anymore. Okay? Next, since energy is scalar, if you're trying to find the total gravitational potential energy of a system, you really just have to find the gravitational potential energy of all interacting masses and add them up together. You don't have to add them up as vectors as you would if you're trying to find like the force, for example. Okay, so this makes this question a lot easier. I'm trying to find the total gravitational potential energy of the 3 masses. That just means I need to find the gravitational potential energy between, let's number them, 1, 2, and 3. I need to find the gravitational potential energy between 1 and 2, plus the gravitational potential energy between 2 and 3, plus the gravitational potential energy between 1 and 3. I'll just call this UG total. So that's the gravitational potential energy of all 3 masses in this figure. We just need to find it for all of them. Now, because gravitational potential energy equation has that negative, we need to remember to put that negative in there. Okay, so we'd have that G, negative G, mass 1, mass 2 over. Instead of just writing R squared, I'm going to write R12, which means the distance between mass 1 and mass 2. Plus, and instead of writing plus, I'm just going to write minus because it would be plus and negative. G, now I'm doing 2 and 3. Mass 2, mass 3 over the distance between 2 and 3. And then plus negative again. So I'm just going to write minus G, M1, M3 over the distance between 1 and 3. And then I'm just plugging in all these numbers. I could factor out the negative G if I wanted. So negative G is negative 6.67 times 10 to the negative 11. And I'm left with mass 1, which was 5 kilograms, times mass 2, which is 20 kilograms, over the distance between them, which is 20 centimeters. So I have to change it to meters. Plus, because I factored out a negative, so I factored out the negative G, so that's gone. Now I have M2, which is 20 kilograms, times M3, which is 10 kilograms, over the distance between them, which is 10 centimeters or 0.1 meters. And then plus mass 1, which is 5, times mass 3, which is 10 kilograms, over the distance between them. How am I going to get this distance here?
Pythagorean.
Yeah, good. So it should be the square root of 0.2 squared plus 0.1 squared. And then when I type all that up, I should get the final answer, negative 1.81 times 10 to the negative 7 joules. Okay, so that's how you'd find the total gravitational potential energy of the three masses. It's not quite as bad as finding the total force acting on a mass, because if I was asking for force, I would have to draw in force vectors and add up the forces as vectors by taking the x and y components and adding them all up to find the total x and y component, and then using Pythagorean theorem to get the magnitude and using tan theta to get the angle or the direction. Okay, let's see what's next. This question, which is what I just explained. So let me see, in terms of video solutions, question 8 has a video solution. So we're going to calculate the answer for question 7 right now. We're going to work through this problem. And then I want you to try question 8 on your own and refer to the video solution if you're having any troubles with it. The answers are written in brackets here, so you'll know if your answer is correct or not. But these get a little complicated because we're adding forces now. So we're back to the beginning of the course when we're adding forces. Okay, so number 7 says, what's the net gravitational force that's acting on the 20 kilogram mass? So here's the 20 kilogram mass. I'll call this one 1, mass 1. Doesn't matter which one's which. So I want the net force acting on 1. So 1 feels a force of attraction to 2, and it feels a force of attraction to 3, okay? We're assuming here that these three objects are just floating around in space and they're infinitely far away from like any celestial body. So there's no force of gravity like acting on them by the Earth or anything. These are just the force of gravity acting on 1, by 2, and by 3. Okay, so we have a force that 2 exerts on 1. Does 2 attract 1 or does 2 repel 1? When we talk about force of gravity, are these always attractive forces or are they sometimes repelling forces, repulsion forces?
Since 1 is bigger than 2, wouldn't 1 be attracting 2?
So does the force that 1 exerts on 2 differ from the force that 2 exerts on 1?
No.
No, think of the equation. The force that 2 exerts on 1 is g times mass 1 times mass 2 over the distance between 1 and 2 squared. Whether I'm talking about the force that 2 exerts on 1 or the force that 1 exerts on 2, the numbers would be all identical, right? And this is the action-reaction pair, equal and opposite. So the force that 2 exerts on 1, is it attractive or is it repulsive? Any two objects, so think of us and the Earth. Are we attracted to the Earth or do we repel from the Earth?
We're attracted to you.
Yeah, all objects, all forces of gravity are attractive forces. No matter what, they're always attractive. Okay, it doesn't matter which one's bigger, which one's smaller. So 1 is attracted to 2. We're looking for the net gravitational force on the 20 kilogram mass, so on mass 1. So we are drawing a free body diagram of mass 1. Mass 1 is attracted to mass 2. So this is the force that 2 exerts on 1. What about mass 3? Is 1 attracted to 3 or is it repelled from 3?
Attracted.
Yeah, it's always attracted. When you take physics 2, you're going to do a similar thing, but you're going to be talking about charges. And then you'll have to think of whether the charges are like charges, then they repel, or are they opposite charges, then they attract. But for gravity, they always attract. Okay, so this one, we would call it the force of 3 on 1. So we're really just drawing a free body diagram of object 1 because the question wants the net gravitational force on the 20 kilogram mass only. So we're doing a free body diagram of object 1. So let's do that. So I'm going to first find out what the force of 2 on 1 is. So it's 6.67. Mass 1 is 20. Mass 2 is 5 over the distance between them, which is 20 centimeters, 0.2 meters squared. Okay, notice the formula for force and the formula for energy are really close. The radius is not squared in energy, and there's a negative sign in front. You're going to get all the formulas. Make sure you don't mix them up because everything will be wrong, of course, if you use the wrong formula. Okay. So I'm getting, so on my calculator, it says 0.000000167. Now there's more digits after this. So if I want to see the digits, I'm going to just type times 1 times 10 to the some number to move the decimal over. So I can see I have 1, 2, 3, 4, 5, 6, 7. I want to move my decimal place over 7 times. So I'm going to times it by 1 times 10 to the 7, and I get 1.6675 times 10 to the negative 7. So the only reason I'm doing this on my calculator is because it stops right here. This is my only view that I can see, even though there are other digits that might exist afterwards. So by timesing by 10 to the 7, okay, that's what I times on my calculator, 1 times 10 to the 7. I was able to move the decimal place over 7 times so I could see what's next, because there wasn't space to see what was next on my screen. So now I can see the force that 2 exerts on 1 is 1.6675 times 10 to the negative 7 newtons, and it's pointing upwards. And then I can do the same thing to find the force that object 3 exerts on 1. So it's the same formula, but I'm talking about mass 1 and mass 3 and the distance between 1 and 3. So I have 6.67 times 10 to the negative 11, mass 1, which is 20, mass 3, which is 10, over the distance between them, which is 0.1 squared. Okay, so I'm going to multiply my number times 10 to the 6 so that I can see more decimal places, and it's really just this 1.334 times 10 to the negative 6 newtons. And this one is pointing to the right. So the next thing is now we want to find the net gravitational force. I have 2 forces acting on mass 1, the 20 kilogram mass. I need to add them up, but I need to add them as vectors. So I have the force of 2 on 1, the force of 3 on 1, and I need to find the F net acting on 1. X and Y. Adding vectors means you need to decompose them and then add them up, add up the X and the Y components, and then put them back together to find the hypotenuse and the angle. So F of 2 on 1, so that was this first one. What's the X component of this vector? It's pointing upwards.
Zero.
Good. And the Y component?
Same number.
Yeah, it's the same number. It's positive because it's pointing up. F of 3 on 1, what's the X component?
Same number.
Yeah, it's the same number. It's positive because it's going to the right. And the Y component?
Zero.
Then I can add them up. This one's kind of nice because there's nothing to add. Times 10 to the negative 6 and 1.6675 times 10 to the negative 7. And then I take those 2 numbers and I put them together. So I have an X component that's positive, which means it goes to the right. And then I have a Y component, which is negative, which means it goes down. So now I need to find my resultant, which is the hypotenuse. So that's using Pythagorean theorem. So this is the F net acting on 1. And it just would equal the square root of both of them added together. And the question wants to know just the magnitude No. So the question wants to know the net gravitational force, which means not only do I have to write down the magnitude, which should hopefully be this number, 1.34 times 10 to the negative 6 newtons, but I also have to find this direction here. So I can say tan theta is equal to opposite over adjacent. And when I solve for theta,
Hey Caroline,
Yeah.
sorry,
That's
shouldn't
okay.
it supposed to be up?
Oh, it's supposed to be up. Yeah, thanks so much for fixing.
You're muted.
Okay. So yes, Khaled was right. I don't know why I made it point down. It should be pointing upwards. So let me move that. The x component is positive, so it's going to the right. And the y component is positive, so it's going up. And so the hypotenuse would still be the same value. And when I find my angle, tan theta equals opposite over adjacent. So I should be able to find my theta here, which is the tan inverse of that fraction. .13 degrees. So my F net would be 1.34 times 10 to the negative 6 newtons. And then how should I give my direction? Think about how the question was given to me with an x and y axis, not with northeast, southwest.
Above the x-axis?
Yeah, good. So it should be 7.13 degrees above the positive x-axis. And that's it. Okay, so I'll give you a chance on your own to just try out question 8. Does anybody have a question about 7? Okay, if it asks for the gravitational force, you need to find the direction as well. So it's not just the magnitude, but the direction as well.